it's a great pleasure to introduce Asghar Ghorbanpour. His title is from Western. His title is A Scalar Curvature of Functional Metrics on Noncommutative Tori.
Yes, thank you very much. Thanks for the invitation, and this is great pleasure to be in this seminar, giving a talk in this seminar. So the title is A Scalar Curvature on of Functional Metrics. This is a work, joint work with Masoud, which is posted on arXiv. Well, these are the parts that I will cover, some quickly, some a little bit more elaborated version. So let me then start with the non-commutative tori. I apologize. I guess this slide is the worst slide of this talk, introducing non-commutative tori in this seminar. But yes, so I have a D by D real matrix, which is antisymmetric, and then we can make a sister algebra which satisfies some universal property, and it has D generators, and the relation between the generators is given by this relation. So the kth generator commutes with jth generator with a phase change given by that, by entries of that matrix. Oh, well, when you make the sister algebra, then there are a few things that comes in. Since I will use this one, at least for the sake of completeness, I will list these two things. One is that we have derivatives, or sorry, derivations on this non-commutative tori, d-dimensional, which are defined on the generator by this relation. So UK, the derivative of UK is UK. Sorry, derivation of jth derivation of UK is 0 if k is not equal to 0, and otherwise it is UK itself. And then this can be extended to a dense subalgebra or star algebra of this sister algebra, and it's going to play the role of basically 1 over I d dxj when we have the regular tori. Basically, the theta is 0, then this is going to play the role of that derivative in that direction. And well, the very important other factor which we will use, this is this tracial state, which is basically integration on this non-commutative space. And the way it is defined is that, okay, if you take an element of this form, it would just pick the term or the coefficient of 1 when you look at the expansion of that element in the spaces powers of u case. Okay, and well, these two things, so integration, differentiation, they have good properties. They respect each other, and that's the property that we have. Okay, so if I set these things, though I have introduced a little bit of differentiation there, but basically with these with this setting, we have a topology. That's what we have, and we really don't want to miss the beauty that geometry can introduce. In other words, I don't want that we confuse a mug with one of these reclining figures by Henry Moore. So we want to bring in a little bit geometry, more how does this work, and so far we are just seeing everything as mug. All those reclining figures by Henry Moore are basically some versions of mugs. Well, to introduce this geometry, well, we don't have access to the old way that Riemann introducing metric and then letting it well, change point to point. But instead of that, the approach which was um, introduced by basically our own community is that we'll use the um, spectral theory or spectral properties of geometric operators, differential operators, in particular Dirac operator and Laplace operator defined by this. I would go a little bit in details of that. Well, if we use that, you'll see in a second that the way everything is set up. If you have Laplacian and you can study this trace of heat kernel, then you can recover some of these geometric quantities such as scalar curvature. This is what we will do here for specific metrics. And while total curvature is also there, well, there is a way to generate Ricci curvature, which is, that's another work that needs another talk to be covered. So we throw out the tensor, the metric tensor, and we start working with differential operators, geometric differential operators, and trying to get information from the spectrum of those ones. Well, in particular, what I mean here is that this is a classical fact that when you have a metric, you can make the Laplacian on the functions, and then form e to the power minus t Laplacian. This is nice operator, well, smoothing differential operator. It's trace class for any positive t, and when you multiply it by a function or smearing factor, sometimes people call, then the whole thing, actually without that, if it is trace class, you can take trace for any positive t. When you multiply if, because that's just continuous operator, you basically get a trace class, and for any positive t, this trace makes sense. But when we let that go to 0 or from the positive side, then we have this nice expansion in terms of t. And the coefficients of this expansion will give us a very nice information about the geometry of this manifold. Well, in particular, we know that every coefficient can be expressed as an integral with some density there, multiply, well, for any function f u, do you multiply it there to that density and integrate. But that density, for example, when n is 1, that density is just constant number. So that will basically Cn will give us just integral of f, a multiple of integral of f. But what is very important for us is that the second term of that expansion, second term is when n is 2 here, so 2 to the power t to the power t minus d. Well, I can write it like that. So if I pick that coefficient of that term, then that will give us one of the quantities that we were looking for as a density of that integral part, okay? And that is basically scalar curvature of our matrix. So that's the scalar curvature. And this is the idea that can be applied in the case of non-commutative torus. And while if we can, so there are a few things that has been done, and we're trying to see what are those, and we did for this new class of matrix, that if we can make sense of a Laplacian in some ways, some good operators we can choose, and we can find the localized heat trace of e to the power negative t Laplacian, then if it has an expansion as t goes to 0, and then the second term, if we pick, then we can say that, oh, this guy here, now for any element from non-commutative torus you put in, it will give me a number. It's a functional, it is linear, and well, moreover, if we can show that there exists an element in T non-commutative torus, that basically that functional is given by the regular integration, or the trace on the non-commutative torus of A times that density, well, that density can be called a scalar curvature, so scalar curvature density here. So this is the idea that is used, was very successful, and for the first time, this was used by Khan, Moscovici, Masoud, and Farzad. So these two papers basically were the first two papers. They were posted at the same time in 2016 of October 2011, and the ideas that I was just giving you was basically developed in here, and the computations were followed up, and the result were obtained. So basically, for the first time, we were able to do, they were able to do compute scalar curvature for non-commutative torus. Well, the metrics were used there were conformally flat metrics on non-commutative torus, and these are the very brilliant ideas all came from that. Okay, so well, I'm just writing one of these the results. Well, I took this theorem from Masoud's and Farzad's paper. So, but this is basically the same result was in the other paper as well. Yes. So here, I just want to show you the result, and then we will go maybe backward. The element that was found there, scalar curvature density R. If you look at the computations, the way it was written, it's very genius idea there, that it was written in terms of this modular operator, log of that, of the commutator of elements with that. But the point was that the whole term, the whole element could be written in terms of some function of the modular operator times the conformal factor, or function of conformal factor, and another function. So these are different formats, and then another term which was like that. Then explicitly everything was computed. The reason that I put this one first, I just wanted to show you the end of this story, that the results in these kind of computation are supposed to be calculated or computed in some form that you can simplify and see it, how the K plays a role, and then the rest of the things are basically hidden in these functions. Okay, and if I want to point out few tricks and tools used in these computation, was the first thing was that, well, how we define that Laplacian or Dirac operator or Dirac square. That was the first thing comes in. But then the next tool, and very important one, this is basically the core of the heavy work done in these computations, is that using Kahn's pseudo differential calculus to generate symbols of parametrics of Laplacian. So that part is also, there are tools, the tools were well developed there. And then at the end, this is the last step, which was very important. And the result of this step is basically what I showed you as functions of some modular operator applied on some elements in terms of that K. Well, if I want to say very quick 2 points that we wanted to generalize this idea was we wanted to generalize this conformally flat matrix. Can one do these computations for maybe a little bit more general matrix? Yes, and in higher dimensions as well. That was another thing. But when we started working, we noticed that this presentation in the contraction form, we actually don't need to wait until the very last moment. We can do right at the first step. And when we start with that idea, then that gives us an ease in computation. It gives us very smooth, and you can go ahead and basically with that idea, we were able to find this, compute some of the scalar curvatures of, for example, conformally flat matrix in all higher dimensions, 2, 3, 4, for any n. I will show you the result. And also we could study a little bit more complicated matrix that we introduced. We call them functional matrix. And yeah, so the main 2 ideas, well, the main step were figured out can be done just by this changing this presentation, the contraction form, and so on. Okay.
Asghar, there is a question in the chat. What is a parametrics?
Yes. Okay. So I can write it here and then delete. That's a good thing. So when you have this Laplacian, you basically want to do minus t here. Yes. But well, to be able to find that that operator, which is supposed to be trace class, we need to compute the symbol of the inverse of this guy, lambda minus Laplacian. And the reason that that is important is that, well, you remember that Cauchy's formula, that if you have e to the power minus well, tx lambda minus x dx, and if you have a good counter, this will give you e to the power oh, did I use x up there? No, I shouldn't use that there up there. So maybe I should put this one here. So this will give us x0. But that is called parametrics. And well, there are subtleties there. We want to define this as a smoothing operator. When we have this parameter t, there we can find expansion for this symbol of 1 over lambda minus Laplacian, and so on. So that's does that answer the question? Maybe should I go a little bit more on that? Okay, that's good. So one of the things that, well, yes, so maybe I should go. So this last thing that we wanted to understand a little bit better, actually later was studied by Matthias Lesch on a very good paper. And well, and he found a way to make sense or make all these definitions that were used very naturally. Make the theory behind that. He developed a nice theory behind that, and well, the naming, the contraction form we will use from there. So basically, what is done is that these are some sort of a functional calculus on tensors of the algebra that you're working with. And here, well, to start with, we introduce this element Hj, which is an element of a tensor to itself m plus 1 times. In the jth place you put h. Everything else you just put 1, then you can well, you can apply this some versions of multivariate functional calculus and make sense of this guy. So f of k0 are these supposed to be k0. So I'm sorry, this should be, maybe I should have written h0 there, but yes, some versions of that will be applied, and then that will give us an element in the tensor. But then we can multiply this element by any other elements of this form. So you check any other numbers, any other elements from A theta, B1, B2, Bn, form this element in the tensor A by itself n plus 1 times. Then you can multiply these two things. Yes, this is an element of this guy, and we can multiply, we get an element again back there.
Oh,
You're muted, I think, Asghar.
So, Asghar, you muted yourself.
Okay, sorry. Is this good now? Okay,
No,
sorry about that. Yes, so we need to do one step of contracting the element that we found, this powers, the tensor powers of A, and go back to A. We started with A, we applied that functional calculus, we found some element in the tensor, now we want to go back. Well, the reason that we went there was that we wanted to make sense of this product here. Now, to going back, we need this contraction map, which basically sends any basic tensor element to the product of the entries that you see there. And while this map extends to the elements that you find by this trick that we used here, and then if I apply that onto what we found, the result will be an element back in A. So this one was, and the way, well, from this point on, when you see that I'm writing this thing here, this will be the meaning of here, this one up there. So it means that first I have this tensor form, I have this functional calculus applied on tensor powers of A, and then we multiplied, and then we contract. So these are notations that was used in Matthias Lesch's paper, and we are following exactly the same steps there. I mean, I'm just reporting that basically. I'm not using any, I'm not adding anything there. Okay. One of the key points, one of the important things about this contraction form is that actually every element that we have of that form can be given in terms of one integral. So we can calculate that thing, and these were basically the main form that was used in the original works. That yes, we were working with those kind of things. Now there is a theory behind that, and well, just makes more sense with these things. But yes, so basically when I'm saying something is in the contraction form, you can see it as an integral of this form over elements of a valued function on Rn, and that's how it is. Well, one of the things that you will notice, well, we noticed this. Well, this is maybe more like a lemma. The version I put it here. There's a longer version, which says that okay, so if you have this closed derivation on your system algebra, and your element H is in the domain of that, let's say it's self-adjoint element, then you apply any functional calculus, smooth functional calculus, and find fh. The result says that, well, fh is going to be in the domain of a delta. Closeness of derivation is here important. But we can do a little bit more, and this is the interesting part, that if you want to differentiate that, find the derivation applied on that element, this will be given in a contraction form. So contraction form becomes very natural when you differentiate a functional calculus applied on one self-adjoint element, which is on the domain of this delta. But this is another thing that, well, I'm using here the notation here is that this is divided, Newton divided differences. Here, basically, when you have a function with one variable, when you find this term, this will be a function with two variables, and it is defined like that. Okay, so then you apply that to h1, h0, and then multiply it to delta h tensor 1, contract it. This is the contraction form. So very basic. First thing, when you differentiate such an element, these contraction forms will appear there. And well, one can go ahead and prove this for any any element written in the contraction form. So if we have very general element written in the contraction form, basically the derivation of that guy can be written in terms of contractions again, and that basically gave us the idea that, okay, we can go ahead from the beginning and start working with elements with differential operators whose symbols are in the contraction form. Maybe I should stop here. Is there any question, any comments before I move? Okay. Well, a few wording about the divided differences, Newton divided difference. Well, the first one is defined just by evaluation. The other ones are defined recursively by this term. Basically, we are trying for the nth one, we are taking the last n ones and going with the Newton's difference and on those ones, minus the first n ones, Newton difference on those ones, and over x minus x0. There's an explicit formula for that, which is given by this. Well, these formulas will become important for us because when we go here, you see that these terms already have higher terms of higher Newton derivations, especially if you repeat this process, differentiate another time, apply the derivation another time and another time, you will get higher orders of this Newton's difference. Okay, so that gave us the idea that, okay, so we can start with those entries, but we wanted to generalize these matrix that was before studied and was conformally flat matrix. The construction of the Laplacian or the Dirac operator was so that at some point we had to use something as the determinant of this matrix of metric. And the definition will make more sense if all these entries of our matrix are functions of same element here. So we fix a self-adjoint element in non-commutative D tori, and then we have basically a metric of this form. So Gij, let me just write it at least on Rn. This is dxi, dxj. So you have those entries of the metric, but now when you're trying to make it a metric somehow on non-commutative tori. So you apply these functions on that self-adjoint element. So our metrics are supposed to be of this form. So if you want to see this in the commutative case when theta is zero matrix, this is basically we are trying to work with a matrix of this form on Rn, well, on Tn. Here, H is in C infinity of TB. So such a metric on Rn will come down and will introduce or will give us a metric or geometry on the D tori. Or sorry, I shouldn't write Rn, Rd. Yes. So these ones, when we apply the steps that were used before for conformally flat matrix, and we start thinking of that, okay, from the beginning, we want to get differential operators whose symbols are in the contraction form, then we can see that the differential operator that we are going to work with is going to be going to have a symbol of this form, symbol of degree 2, degree 1, and the degree 0 part. And each one is given in the contraction form. So you see these CIs are coming from RD, but the rest are elements from A theta, and those are given in contraction form. And while these can be calculated in terms of the metric that we started to work with, so this functional metric. So this calculation can be done now thanks to all the tools that are now available. And while we can go ahead and try to mimic again the same steps and try to find the parametrics, trace of the heat kernel, and so on. But before we move on, we saw that all the calculation we are doing there, well, there's no reason that I fix what are these guys here. We don't need to fix those ones. We can go ahead and try to see in general what are the symbols of parametrics of operators with these kind of symbols. And well, some work there done, but the good thing is that with this fixing notations of bringing up the contraction form to the first step, so you start working with differential operators whose coefficients are in the contraction form. Basically, everything you get this side of symbolic calculus. For example, we can use, as you see here, we can use Einstein's summation notation here now, like the classical calculations that we do for the matrix. Also, you see that how does that help? Now we have those ones also here. This is just very small piece of that. That helps us to calculate all those terms that we are looking for. And for general such operator, we can compute those terms. So B2, remember that B2 was the term, the second term at A. Remember that phi at A of B2 was like that. So in the classical case, this was when you use the Laplacian, this is supposed to be the scalar curvature. Now we can calculate those for any positive Laplace type differential, H differential operator. We call those ones H differential operators. And well, the calculation now can be done in very general form. And these terms, these functions are in terms, or we can find them, and they're in terms of the original symbols that we started with. Well, there is a small lie there. These functions that appear in this These results, these are given in terms of some integral. So these are, we have integral form of those ones. Well, this was another term there. Sorry, let me just move here. Those functions, this is now we are working with multivariate functions. For those ones, we could simplify all these integrals, all the terms that we wanted to calculate, and we ended up with one integral like this. And these integrals can be calculated for some values explicitly. So we can find, this is a function. It has an integral form, defined integral form for any given symbols. If you can calculate those ones, you have the B2 term, the second density of your, the density of the second term of the expansion. Okay, and well, then we want to turn this handle for the cases that was done before. Yes, this is conformally flat metric that was done. So in the conformally flat metric, all the entries of the metric, these are multiple, constant multiple of one function. Well, the notations are a little bit different than the one was used originally in the conformally flat case, but with very simple change of things, you can get those results out. And for those ones, actually, we can calculate those t functions, and those are given by higher Newton differences of function, very simple function, u to the power 1 minus d over 2. Okay, and well, using that, now we can find the density for the second term, and for and well, we call that scalar curvature density. Yes, and that is now given in this form. Note that I didn't restrict my dimension to 2. This is for all dimension, for all dimension of for all dimensions. So this trick of turning everything from the beginning to the contraction form give us this ease of calculation that we can go ahead and calculate all these terms. And yes, so well, see that these two terms, these terms down here, these depends on f. The other ones are just functions of f, and those functions are given here, which reduce. Okay, so these calculation that you see here is for d not equal to 2. For d equal to 2, similar calculation can be done, and it will give you the result that found before. But you see now, just for 1D, you replace D, you can find the term for 4-dimensional and so on. So for any dimension that you want. But that trick doesn't stop there. We can actually calculate those T and alphas for other kind of metrics. One specific form of these metrics is a twisted product of flat matrix. It is again a functional metric. We could fix those ones and calculate all the works that we needed to do. And again, that general machinery will give us the results. Here, why do I have the theorem? Yes, so this theorem is the original theorem that I mentioned, that for any H differential operator, we can calculate that B2. Well, we can calculate those ones, and the results are, again, in some nice format, which originally was found for 2-dimensional case. And we can go ahead a little bit more. We can find integral of the scalar curvature. Well, in the classical case, that's integral. Here we can find phi of the integral, the curvature, scalar curvature, we called it, well, it is called, not we, it is usually called total scalar curvature. And here we can calculate this again for all the for all the functional matrix actually. And one good outcome of this thing is that when we go to the dimension 2, we see that the total scalar curvature for any functional metric you fix on the two-dimensional non-commutative tori will vanish. And that is some version of Gauss-Bonnet here, meaning that the total curvature is independent of the geometry you choose. Just wrap up starting with the idea of differential operators whose symbols are written in the contraction form, and developing that simple calculus that, well, differentiation of a function of a smooth element is in the contraction form, and working on that gives us, first thing is that we can calculate the scalar curvature density and total scalar curvature for conformally flat matrix for all dimensions. So this can be done for all dimensions in one shot. The second thing is, while we can do a little bit more, for example, twisted product of flat matrix, we can also calculate the scalar curvature, the density, and the total scalar curvature. And, well, the total scalar curvature for the case 2 before dimension 2, it was only proved for the conformally flat matrix. Now we can prove Gauss-Bonnet theorem for more general functional matrix. And that brings me to the end of the talk. Thank you for your attention, and thank you for being here. Thank you.
Okay, thank you.
Thanks. So any question, any comments now?
Well, I have several comments. I mean, you know,
Sure.
well, okay. So, you know, first of all, I mean, the initial development, I mean, it came from very, very long ago. It came from the end of the 80s, in fact. When, you know, with Paula Cohen, we computed the curvature and so on in the conformally flat case. And at the time, we were computing by hand. So I mean, we obtained a result which we didn't dare to publish because the result looked you know, a little bit complicated. And then what happened was the following. What happened was that I met Paula Cohen again in I think it was in Johns Hopkins for some conference, and then we decided that we should, you know, look again at this paper. And, you know, since I spent my time worrying to have made a mistake somewhere, one night I was very, very worried because I realized that using some work I had done with Ali Shamseddin, I could prove that the Gauss-Bonnet had to be true in this case. So then I looked again at what we had computed with Paula, and I was amazed to see that indeed the total curvature was 0. But I mean, this came, if you want, as a big relief of some worry which I had. And that was the reason why we actually wrote the paper. So we wrote the paper because, if you want, we were very pleased to find out that the total curvature was 0. We had only done it when the conformal modulus was equal to I. And then, of course, Masoud, and you know, he did it in general, I mean, with arbitrary tau. Now, the second point which I want to make, which I think it's important to point out the nuance between the two papers that you presented at the beginning. I mean, the paper of Masoud and Farzad and the paper with Moscovici. I mean, the point was that again, if you want, in the paper with Moscovici, we had found abstractly that there had to be some very non-trivial identity, which had to be fulfilled between the function of two variables and the function of one variable. And then again, you know, okay, I was extremely scared when I went to the computer and I asked my computer, is that true? Because the point is that with these formulas, you can actually, you know, you can use a computer and the computer can tell you whether it's true or not. And miraculously, again, if you want, the computer said, yes, this is true. So in that sense, if you want, there was a very powerful means of checking that some formulas, which otherwise are very hard to test. I mean, how do you test these formulas, except for Gauss-Bonnet? I mean, they are very, very hard to test abstractly. And then the reason why I explained that is that then with Farzad came to Bure in the beginning of the 1910s, I mean, you know, around perhaps 1912 or something. And I mean, we decided with Farzad to compute the A4 term for the two torus. Now, the point is the following. The point is that the reason why we did that was that we knew that in dimension D, the interesting term is A sub D. So of course, for the non-commutative two torus, it was just A2. But what one can do, is take the product of two two-dimensional tori, and look at it as a four-dimensional torus. And if you look at the generic case of the product of two conformally flat two tori, the result is not is not conformally flat. It's not conformally flat. And so what we did with Farzad was, again, I mean, Farzad developed fantastic, powerful computer tools, and I mean, and it used really the power of an auxiliary computer. And one day he found out that the relations which he had extended, you know, the relation we had found with Henry, which were finite difference, of course, they are related to this Newton calculus, obviously. And so he checked with the computer, and the computer took some time to check them, but they were true again. So now the new feature, which I want to insist on, is the fact that when you look at this non-conformally flat four torus, what happens is that you don't have just one modular automorphism, you have a pair of modular automorphisms. And what is sort of, if you want, lying in front of us is a situation in which one will extend the modular theory to the situation where you have a general matrix. I mean, I think Jonathan Rosenberg defined general matrix in some way. And so I think, you know, it's very important to extend, because what you have done, if I understand correctly, you were taking all your Jijs to depend on a single element.
Yes. Yes.
So that's a rather still, I mean, so one test that you would have to pass, you would have to prove by doing these calculations of curvature and so on, that one of your metrics is not conformally flat by studying an invariant. Namely, you see, what I'm saying is that even, so do you know that, for instance, in the two-dimensional case? No.
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 Yeah.
So I think if you want, it's quite important to develop new invariants, okay, which can use the structure which is available, and show by, you know, by a theorem that by using your computations, of course, that the new metric that you have is not equivalent to a conformally flat metric.
In the higher dimension, you mean? Yes.
This is what I mean. Even in two dimensions, yes, even in two dimensions.
Oh, I see.
And so if you want, then okay, there will be several ways to go for general metrics. I mean, one is the, as I said, I mean, this is proposal by Jonathan, and one should construct the corresponding Laplacian. But there is another way, which is to change the conformal structure, as I was doing in my book, by using Beltrami differentials. And there, for instance, if you want, one would have, for instance, to classify the conformal structures and so on and so forth. And I'm sure that, you know, there is remarkable things which are waiting for us. But so if you want, okay, I find of course these computations are very well done, extremely streamlined, and the generality is beautiful. But somehow, you know, I think you would need to make one more step in order to confirm that and I don't think it should be too hard, because somehow, you know, you have done all the calculations. So now, okay, so one has to find a property of the conformally flat matrix which is not shared by this matrix. And I mean, might be it has to do with the higher terms in the computations. I don't know. I have no idea. I mean,
yeah, sorry, just to add to that. So we started studying these ones in the classical case to see, okay, so in the classical case, at least they should give us more general thing, yes?
Okay. And,
yeah.
And what did you do in the?
Well, we haven't been able to find any invariance there, but definitely, for example, in 3-dimensional, there are metrics we can show that there are examples that are of that form, but not conformal.
I understand. Yes.
No, sorry. I mean, in the classical case, in 2 dimensions, of course, because of uniformization.
Yeah, exactly. They are all of the same.
Every metric is conformally flat. I mean,
sure. So there is no way in 2 dimensions. Yes.
Exactly. But what Alain suggests is very interesting, even for dimension 2, because it's in the non-commutative case.
Exactly. I mean,
because we don't have uniformization, and that's what he suggests. That's exactly the point. I mean, we can do and kind of, if you understand this question, we have some steps towards non-commutative uniformization.
I think Jonathan wants to speak.
Yes.
Yes. I was just wondering if I could ask a couple of questions. So, just to sort of follow up on what Alain was bringing up, I'm not sure, there's some basic questions even in dimension 2, which I'm not sure were ever settled, and I'm kind of curious to know if you know anything more about them. So one, of course, is, so Alain proved this Gauss-Bonnet theorem, I mean, with Paula and then with Henri, that the total scalar curvature is always 0 for conformally flat metrics. So one way to show that you don't have uniformization would be to find an example of a not obviously conformally flat metric for which the total scalar curvature turns out to be non-zero. I don't know, has anybody ever made any progress with this?
Well, it is 0, unfortunately.
Oh, it is always 0. Okay. That's for a functional metric. No, I meant a non-functional metric. That's the
general. I mean, when the elements do not commute. I mean, we don't.
Yes, when the elements don't commute. Right.
No.
Yeah. So another question sort of related to that is that there's one other paper in this subject that doesn't seem to fit into this sort of line of development that you're talking about. And I'm not sure how to fit it in. And I was wondering if you've sort of studied it and tried to think about it. So there's this paper by Dabrowski and Sitarts, where they consider these sort of funny looking metrics on the 2 torus, which are definitely not, they don't look conformally flat when you sort of look at the picture of them, but you know, maybe they are, you know, it's sort of hard to tell. And they do some calculations, and for those things, they also found out that the Gauss-Bonnet theorem seems to hold. In other words, I
have one remark, Jonathan, on what you just said, which is that in the paper with Henri, we gave a conceptual proof of the Gauss-Bonnet without calculations. So this could be the root which is behind it, actually.
Right, but was that only for conformal metrics or for arbitrary?
No, I mean, if you want, the idea of the proof, which is conceptual, was not especially for conformally flat. I mean, it was a general idea.
Yeah, but I'm not sure if it's. Yeah. But does it apply to a completely arbitrary metric?
No, I mean,
that's.
Yeah, if you want if we want to attain arbitrarily, I would even start with the conformal structure, because what one knows is that the ways that the conformal structure are usually obtained by Beltrami differentials extends to the non-commutative case in a perfect way. So I mean, if one could do calculations at the conformal level, that would be already, you know, a big step, because somehow, if you want, at the conformal level, there is a beauty, which is that there is a canonical inner product on one forms, which is coming only from the conformal structure. So somehow there is room there, and the formula for the perturbation of the conformal structure by Beltrami differentials is a beautiful formula. It's a formula which uses von Neumann algebras and which replaces the F operator, which is of square one, by a rational fraction AF plus B over CZ plus D. I mean, we have to be careful about the order of terms, of course, because it's non-commutative. But so if you want, there I think there is a lot of room for experimentation. And but of course, one should also use the way you were considering the matrix, and one should obtain the related operators and work with them. I think this is a very important strategy now, because somehow the matrix that Asghar was considering, they are a little bit limited as related to a one-dimensional situation. They are kind of pulled back, if you want, of a one-dimensional situation.
Yeah, so I had a method of defining general metrics. So you could have a general metric was basically a, you know, any positive definite matrix over the algebra.
Yeah.
But the problem is that it's almost impossible to do any calculations unless
well, you see,
reduce it down to a
no, you are right,
something like your functional situation.
Yeah, you are right. But on the other hand, you know, this is what I thought 30 years ago when I was working with Paula, that it would be impossible to actually go further in the calculations and so on. And this, well, I mean, you know, with the computers and so on, they push the limits very far, very far. So I think what one needs is to experiment with non-commuting specific operators and so on. Okay, I mean, and experimentation should be possible, actually, I think. I mean,
one problem with this more general metrics is that when you do things, I mean, they don't form, I mean, the algebra of differential operators in this case, like Laplacian, they don't, I mean, there is no standard form for elements.
No, but wait, Masoud, what I don't understand is, can't you use a metric as defined by Jonathan to define
you can, I believe you can take that, and then as you did, like by defining the adjoints, because you have
then you should have an operator. I mean, you know.
Yeah, definitely, we have an operator, but we don't have a standard presentation for elements, like when you have the algebra of, you know, differential operator, like Weil algebra, you know. Like, so what is lacking is normal ordering, essentially.
Okay, fine. But
no canonical normal ordering. So you lose control. I mean, so the differential calculus is very hard to get at in this case.
Yeah, okay, but I mean, at least the problem is well defined. Okay.
Yeah, the problem is well defined. Absolutely well defined.
Yes. Okay, then
the problem is well defined. Absolutely. Yeah.
And
by the way, Alan, sorry, go ahead.
No, let me just add one word. You see, the reason why I believe it's so important to look at these general cases is that in general, it won't be a single modular automorphism or single modular theory, as we show with Farzad, if you want, in the four-dimensional case. So in general, what it will be a kind, instead of being the modular automorphism given by an action of R and so on, it will be an action or a for instance, of a non-trivial group. And for that reason, of course, the problem looks very complicated, but for that reason, I think it's extremely interesting. Because you see, when you consider, for instance, the case of foliation, this extended modular theory does exist. So it is probably there behind the scene. And yes, of course, very difficult to find, but as long as the problem is well defined, fine, okay, you know. Then,
by the way, your proof of Gauss-Bonnet using perturbation arguments in paper with Henry works in many general cases.
That's what I was
suggesting. It's a very general idea,
yeah, it's a conceptual idea, which is very
a conceptual idea. It can be generalized in many cases. Yes.
Just can I add a point about the Jonathan's question about the Sitar's and Dabrowski's work?
Yeah, that's a special
So
case.
there were two things there. Actually, in some conference, I talked to CTARs about this thing. One is that the calculation they have done is in a little bit different form. Like they are doing some kind of perturbation and they are calculating the second term in that calculation. So it is coming from a different point of view. But if I'm not wrong, this was a little bit long time ago, that their metric is basically that twisted product of two non-conformal flat matrix. So it is basically covered somewhere here. Sorry, in this one, the twisted ones, the twisted product. So the one direction was not symmetric. That's now I remember that one. So this, I believe, covers that result as well, the spectral formula.
Yes, but what you say, in fact, suggests one thing to do, which is to do perturbation theory around the classical case and in the non-commutative framework. I mean, you know, this should be much more accessible somehow. I mean,
I see. Yes, it should be. Yes, you're right.
Okay. Well, thank you.
Thank you for the comment.